To everyone. So our exam tomorrow is going to be over chapters 13, 14, and 15. That is, we're going to be studying the thermodynamics chapters. So I really want to see scores go up because some scores weren't as high as you would hope for. So the things that are in each chapter, I only have 3 slides, one for each chapter. So chapter 13 was our first chapter on thermodynamics, and we start off with just defining temperature. We have the 3 different temperature scales we've used. You could have a problem as simple as converting temperature, although that's unlikely. What's much more likely is you might have a problem that says the temperature is this many degrees Fahrenheit and then asks you to do something with it, and you'll have to just know, well, I can't use Fahrenheit with any of the constants or whatnot. I need to convert it. So we have the 3 temperature scales that we use commonly. Fahrenheit only used basically by we in America, I believe. I don't know of any. There's got to be at least one other country that uses
There's
it.
Like
one island nation with a population of 50, and us. Celsius. Remember what the reference points are for. Well, instead of 0 degrees Celsius, now it's 0.01 degrees Celsius. You might remember that I said that wrong before. I said 0.15 or 0.16. I said 0.16. It's 0.01 degrees Celsius is the triple point temperature of water, and 100 degrees Celsius is the boiling temperature of water. Both, well, the boiling temperature has to be at 1 atmosphere. The triple point just has to be pure water, and you're good. Kelvin is just shifting the Celsius scale to an absolute scale, a scale that 0 degrees Kelvin corresponds with absolute 0. Now, by this point, we've studied about the Maxwell-Boltzmann distribution and the kinetic theory of gases, so we know that in theory, absolute 0 temperature would be 0 average kinetic energy for the molecules. So, in practice, it doesn't quite work out that way because of quantum mechanics. But, that's what 0 means. That's why there's an absolute 0. So make sure you're familiar with those scales. Obviously, you'll have the equations to convert from one temperature scale to the other, but you still have to know when to do it and how to do it. A number of students sent me questions over the last few days about either the review assignment for a tiny amount of extra credit or the homework assignment that's due tonight that's over material to be on the test. So I'm going to leave it due tonight because it's on material on the test. And I don't know if the students made this mistake or not, but the problems that I was asked about, a lot of them required you to shift from Celsius to Kelvin. It doesn't say shift from Celsius to Kelvin. It says the temperature of the person in the all-white suit is 9.7 degrees Celsius. And the temperature in the environment is minus 14.5 degrees Celsius. And then it asks you to find the rate of heat transfer. Well, for that rate equation, which is going to be on chapter 14, I think it's chapter 14, you have to use kelvins. So I had to shift it from Celsius to kelvins. Now, while I'm on that, I believe that's problem 10 on the review assignments. There are actually 3 problems with it. The first 2 probably everybody just glossed over, may not have even noticed. So the first problem with, excellent. That's obviously the wrong tool. Number 10 on review assignment. It says temperature 2 equals, and it has minus in black, and then something like, 14.5 degrees Celsius in red. And then down below, when it shows a summary, it'll say temperature 2 equals, and it just shows the number in red and doesn't show the minus sign. It has the minus sign, so that's a typo that it's missing the minus sign that goes right there. If you just read the text of the problem, it's going to be fine. But if you look at the summary of variables, which I do, it has it listed incorrectly. Second, and really more humorous, is it lists the area, the surface area of the person, as something like 1.35 meters squared. And then when it lists the summary of the variables, it says the area is equal to 1.35, and then it has degrees Celsius. Kind of an obvious error. I doubt that's going to trip anyone up. The third problem is one that would trip everyone up. There's no way you're going to get it right because of the third problem. So the third problem is that it asks the rate of heat emitted by the person or lost by the person, something like that. I don't remember the exact words. And if you say the rate of heat loss, that means it should be positive if heat is going out. Since the person is hotter than the environment, the heat should be going out. But they want an answer with a negative sign. Right, so they have the wrong sign on their answer. So when I was doing this morning, as you asked me, right? When I was doing this morning, I did the calculation, I got my number, I put it, it says it's wrong. I'm like, how could it be wrong? The first thing I did was change this temperature by changing the sign in case that was the case. No. Then I flipped the signs, got around, and finally found that their problem was that they had an answer with the negative sign. So that one, you just have to know there's a problem there, which is why I'm telling you. Since I've gone through half of this, question?
If you're defining the person as the system, though, is it like QH positive and QC negative? So like heat going out of them, wouldn't that be negative?
The problem says the rate at which heat is something like heat is lost by the person. So if it's the rate of heat loss, then it's positive if heat is lost, right? Because it's specified with the words, it's specified and it should have had a positive answer. But they're going with a negative. Since we've gone through all this, let's finish off the problem. How do you find the rate for heat loss? Well, I don't think the problem actually says which type of heat there is or involved here. There are three types of heating. They're right here: conduction, convection, and radiation. If I have a person that's standing out in the cold, what method are they going to absorb or lose heat into the environment? There could be some convection, but that's going to be because they're wrapped up all nice and tight, not the primary method. Also, and this is really important for test questions, we don't have an equation for the convective heat loss. So they're not going to ask you about the rate of convective heat loss or gain because we don't have an equation for it. So we'll rule out convection because we don't have a way to calculate it. So then you have either conduction or radiation. Which would it be? Radiation. Even though auto answer is off, it still kicked us off. I will have to talk about that with our tech guys again because it's not supposed to interrupt us when the auto answer is off. Okay, so you have conduction, which is transferring heat because of physical contact, or you have radiation, which is sending out electromagnetic rays. So if the person's standing here in their suit and we're talking about the environment, they don't have physical contact with another object, so it's going to have to be radiation. And so using radiation, we have our equation is heat per time. Notice technically we don't put a delta in front of the Q because heat is not something that anything can have. Heat is a transfer of energy. And so Q is actually already a change. You don't put delta Q because that would be change and changing. Yes. That's equal to the power, and we have our simple equation. That's the equation for heat absorbed or emitted. And so if I want the net heat, so the power net, and you might ask, how do I know which temperature to put first? Well, if it's the power that is going to be emitted by an object, then you put the temperature of the object first. If it's the power absorbed by the object, then you put the temperature of the object with the negative sign. So in this case, I'm going to have, since it's the lost, this will be the temperature of the person and temperature of the environment. And so we put our numbers. The Stefan Boltzmann constant, I don't remember. That's okay. We're just going to leave it with the symbol. The emissivity, you were given in the problem an emissivity. Emissivity is how efficient something is at absorbing or emitting radiation. It's the same efficiency for absorbing or emitting. It has to be somewhere between 0, which means it absolutely doesn't absorb or emit. What color would typically be identified with something that does not absorb or emit? White. Better yet, silver. Why silver? Well, what happens to light when it hits a silver surface? It reflects off. White, you can at least see the surface, so it's not reflecting as much. So silver is the best, just like the silver and black. What color is the best for absorbing?
Black.
Just like silver and black. We've won 2 games since we last saw each other. It's what? Well, yeah, they beat the silver and blue, didn't they?
What?
Isn't that Carolina? Oh. Well, what color is Carolina? I thought they were silver and blue too. Okay. So, staying off of that, so the emissivity was given in that problem to be 0.200. The area was the surface area. Everybody's going to have a different area, so I'll just put that in there. And then you have the temperature of the person. I have written here, well, I don't have temperature of the person, but the temperature of the person, at least in my case, was, temperature of the person was, I think it was 9.5 degrees Celsius. So what do I put in there for temperature of the person? In kelvins. I have to know to convert that to kelvins. So I take this and add 273.15. Remember, kelvins doesn't have a degree sign. And so I'd have 282.65 kelvins raised to the 4th power minus, and then the temperature of the environment, minus 14.5. So 273.15 minus 14.5 would be, I don't know. Stop that. This way. Somebody who did it for me. Is that right? It's something like that. And so that's how you calculate the answer. Was it right?
Yeah.
Okay. So that's how you calculate the answer. You're going to have different areas. You're going to have different temperatures, but I showed my temperatures in there just so you remember, yes, have to change it to kelvins. So I did all of this to remind us about the temperatures, temperature scales. So next thing, what happens to most materials when you heat them up? Besides they get hot. They expand. Good. Name something that doesn't do that. Water, right. I'm sure there are other things besides water, but it's very rare. Water's the one we know. It's important that water does the opposite thing because that allows us to have things like lakes with ice floating on the top and water underneath so the fishies can swim around and not be stuck in there. Now, I know there are some fish who can be frozen and thawed, but it helps to keep us from getting into a deep freeze on Earth, that water does that. It also helps to do cool things like break pipes in your lawn or in your house because you have the water. When the water freezes, it expands. You have the metal. What happens to the metal when it froze? It contracted. Well, those are going the wrong direction. And so you have something pushing out, something pushing in. You have a stress, a force per area. And if that stress becomes larger than the ultimate strength, it bursts. And that's bad. Question, Mahala.
So when water in its liquid form is heated and it becomes a gas, does that still count as an expansion?
Actually, water is its smallest volume at, let's say, 4 degrees Celsius. Rounding off to one significant digit is 4 degrees Celsius. It's like 3.9 something. So that's where water is the most dense. It's the smallest volume. As you heat it or cool it from there, it expands. And if you change phase, of course, going from liquid to solid, there's a major expansion there. When you boil it, it'll fill whatever environment you give it. So it's kind of hard to do the same kind of calculation there. Okay, so we have that expansion, just the simple relationship that the change in the length of an object is equal to some parameter that we call the coefficient of thermal expansion multiplied by the original length multiplied by the change in temperature. So the units of that coefficient, it's unitless. There's no units in alpha. The units of, oh wait, I take that back. It's not unitless. It has units of 1 over temperature. Yes. Units of length, of course, length. Units of temperature, what unit should you use for temperature here? Kelvin or Celsius. Because it's a change of 5 degrees Celsius is exactly the same as a change of 5 kelvins. So in this equation, it doesn't matter if you use Celsius or kelvins. You won't be wrong, though, if you use kelvins. So, if in doubt, usually the kelvins is going to be the choice to go to when you're in doubt. If you know, well, go with what you know. For volumetric expansion, it's just the same, except for you have a different coefficient for volumetric expansion. And as we showed in class, and as a general rule, that beta coefficient of volumetric expansion is pretty much 3 times the coefficient of linear expansion. So make sure you can do problems with that. Things like, I have a slab of concrete that's this long, and my temperatures range between, well, here in Lincoln, what's the coldest it gets?
Like -20. It can hit like negative 30.
Yeah, let's just go with -40. You know why? Because that physics joke, -40 is the same if you're Fahrenheit or Celsius. Let's say it gets down to -40. That would be the absolute coldest it should get here. Hottest it gets here?
110.
It's so wonderful. Okay, so 110 in Celsius, that's about, let's say, 45. So we're going from about -40 to about +45. So that's a difference in temperature of 95 degrees Celsius. And they say we have a slab this long. How big of a gap do I need to put between one slab and the next slab? Well, you say, how much could expand or contract? You want to take the difference between its minimum and its maximum, make sure the gap's that big. Okay, molar and atomic masses. I didn't spend a lot of time on these, but they are important concepts. The mass of a mole is just Avogadro's number 6.022 times 10 to the 23rd molecules. And so the molar mass is the mass for that many molecules. Whereas the atomic mass is the mass of one singular molecule. So different problems will have different variations on that. When we got to the kinetic theory of gases, and we had an equation that said the speed RMS was equal to square root of, and I think it was 3 kT over m. I don't have that memorized, so I could be wrong. What m do you have to use there? It's going to be the mass of a single molecule. So it's important to know the difference and to be able to identify an equation, what you're using. On the test, there was a problem that had to do with the viscosity. Do you guys remember the problem where you have a tube? This problem I have to grade differently for the Southwestern people because it did not give you the elevation of the water, and you have to know that to solve it. So everybody there at Southwestern, know I'm going to grade yours differently because you didn't have that elevation. It's supposed to be a ½ meter tall, but it didn't say so in the problem. So because you had that water ½ meter tall, you had pressure 1, pressure 2. Pressure 2 would be atmospheric pressure. Pressure 1 would be atmospheric pressure plus rho GH. And then, of course, you had the length and the radius. And the equation that you use to calculate the viscosity from this is that the flow rate is equal to, oh my goodness, I know I don't remember this. I think that's the equation. And so you had to use that equation to solve for eta. There were a number of people who used another equation, the definition of viscosity, and then they called that V times A the flow rate. But that's not what it is. V times A is the flow rate, but that's the speed of the fluid times the cross-sectional area of a pipe. But in this equation, that A was the surface area. You have two sheets, each with surface area A, and V is the speed that one of those sheets is moving with respect to the other, and L is the separation between them. So the variables in this equation did not match up with the variables from this problem. Hence, it wasn't applicable to the problem. So you need to make sure when you look at equations, it's not going to tell you which area A is or which mass M is. You have to know those pieces. Okay, a lot of noise already on my sheet. Ideal gas. If we're going to work with ideal gas law, it's important to know what an ideal gas is. You know, I remember when I was in high school, my physics and chemistry teacher, same person, of course, talked about ideal gases, and I was like, well, it's ideal, the end. Doesn't really help me, because how do I know if a gas behaves ideally? I have to have some understanding of what it is. So we had two basic things that an ideal gas had to have to be ideal behavior. What were those two things? Okay, we had to have elastic collisions with no interactions unless they collide, and no volume. No volume isn't possible, but if it's low density, that's approximately no volume. And so that's an approximation. So when I have a gas that's in a low density situation, then it's more likely to behave ideally. And of course, the molecules are always going to have some kind of interaction when they collide, not be perfectly elastic. But the faster they're moving, the smaller the energy they lose in the collision is going to be compared to their overall energy. So the closer it is to an elastic collision. And what property tells us how fast the molecules are moving? Temperature. So if they're moving fast, if they have a high temperature, it's more ideal. And in a practical sense, we say if the temperature is well above the point of liquefaction, that is well above the temperature where it would condense into a liquid phase, then that's high enough temperature. And then there's not a similar rule of thumb as far as I know for density, just if it's a relatively low density, it's ideal. We had 4 laws that different physicists put together to describe the behavior of ideal gases from experiments. And from those 4 laws, we can combine them all into one law, and so that's why I have the ideal gas law in red. I am really, really, really unlikely to ask you about Charles' law or Boyle's law or Gay-Lussac's law. I will ask you questions that might be answered by those, but that would also be answerable just using the ideal gas law. So you really only need to know the ideal gas law and know that the ideal gas law was built up from these experiments that gave us the other 4 laws. We had those variables of state that were in these laws. What were the variables of state? The variables that are related in the ideal gas law. So you said? Pressure, volume, temperature, and one other. The number of moles or the number of molecules. That's interchangeable. We later on learned a 5th variable of state, and that was the entropy. So those are our variables of state in physics. In chemistry, I believe you'll have at least one more, but in physics, we limit ourselves. Something we really do in physics a lot is we say, we can put things in a closed chamber, so let's do that. In chemistry, they're all, well, I have to pour this into that, so it's going to be open to the environment. And that makes it more complicated. Okay, kinetic theory of gases. Remember, I went through that derivation. You obviously won't have to do the derivation, but you may have a question about something like the RMS speed and how that relates to temperature, or how the average kinetic energy relates to temperature, things like that. So make sure you understand the outcomes. of the kinetic theory of gas derivation. Humidity, we did just a little on humidity, so I'm not going to ask you any questions on humidity or evaporation or even boiling. We did cover them, but not enough for me to feel secure that you should have good knowledge about those. And last thing I want to do is ask you questions that I expect you don't know the answer to, right? So that's chapter 13. Chapter 14. Make sure you know the difference between heat and temperature. A lot of times, especially before you've taken a physics class, you just basically think temperature and heat are the same thing. I mean, if it's hot in the room, I turn down the heat and it gets cold. So I identify heat with temperature. But what is heat? It is energy being transmitted in or out of a system. And temperature changes in response to the change in energy. And so we had things like the specific heat. We related the heat going into or out of an object is equal to the mass of that object multiplied by its specific heat multiplied by the change in temperature. Change in temperature, what unit should you use for temperature? Celsius or Kelvins. Doesn't matter. Either way it'll work because it's a change. M is the mass of your object. It's not the molar mass. It's not the atomic mass. It's the mass of your object. And C is specific to the object. So if it's steel, it's going to be 1C. If it's aluminum, it's another. There was a problem that another student asked me about. Actually, it might have been the same one. That had to do, nope, it was Courtney Hanna that asked me. A question about one of the homework problems that's due today. And that homework problem was about lava, or magma, that cools, freezes, and then cools some more. And it asks you about the change in entropy of the lava and of the water as it goes through those problems, or those transfers. So this Q equals MC delta T, that's how we can calculate the heat that is coming out of the lava as it cools. But then when it starts solidifying, when it goes from liquid lava to solid rock, what's the equation I have to use then? There's no T, no delta T, because the temperature is constant during the change. It's going to be the mass that changes phase multiplied by the latent heat of fusion, because it's the one that has to do with solid-liquid interface. So you have two different heat equations depending on which of the transitions you're looking at. Now, the student didn't ask me about those pieces. The student, right, this homework is useful for reviewing for the test. So the homework is due today, that is assigned for today. What the student actually asked about was the calculation of the change in entropy. We talked about what entropy means. Of course, that's on this, the last things there. We talked about what entropy means. We have two definitions, both correct definitions, not describing different things. One, the statistical definition about the entropy is Boltzmann's constant multiplied by the natural log of the number of microstates in the macrostate, a statistical number. And one that says that the change in entropy is Q over T. Why is there's a delta on the left side, why no delta on the right side? Because Q is already changed, right. So we have that equation. If the temperature is constant, we use this equation. But of course, when you are cooling the magma from its initial temperature of over 1,000 degrees Celsius down to 700 degrees Celsius, the temperature is changing. It's not constant. And so I can't use the equation that way. So we worked out in class on Wednesday last week that for a situation where this applies, you have to use that equation. That the change in entropy is the mass multiplied by the specific heat multiplied by the natural log of the final temperature divided by initial temperature. Question?
Both those equations will be available to us?
On the test, yeah.
gonna put the equation sheet online before the test?
I will try to, yes. I've been spending all of my efforts trying to grade old tests and haven't thought ahead yet. Okay, what unit should I use for temperature in this equation? Kelvins. Why do I have to use kelvins here? Why can't I use Celsius? Because it's a ratio. And if you just think about this in a very logical sense, if I went from 0 degrees Celsius to 100 degrees Celsius, my ratio would be 100 over 0, and that's infinite. But if I put it in kelvins, it would be 373 to 273. That's, less than 2. So you can see there's a very big difference, and in that case, you have to use the kelvins. Okay, so we have the equations there for the specific heat that relates the mass, the change in temperature, and the heat. If we have something that's solid or liquid, if it's a vapor, we have a slightly different version. If it's a vapor, we still have a specific heat, but we have two versions. We have Q for an isobar is equal to NC sub P delta T, and Q for an isochore equals NC sub V delta T. The C sub P means the molar specific heat at constant pressure. C sub V means molar specific heat at constant volume. When I say molar specific heat, that means it's the heat per mole per degree Celsius. So in the top equation, that was a mass specific heat rather than a molar specific heat, because it was the heat per mass per degree. What happens to the temperature during a phase change? In theory, it stays the same. In our practical experiment, it didn't, right? And I said there might be a couple things that I want to explore, things like the thermometer had most of it not in the liquid, and it could have been, heat traveling through the thermometer causing some variation to show up. In theory, it stays constant. If it's not perfectly pure, that theory is broken. It will change temperature a little bit. I remember in organic chemistry lab doing experiments where you're actually measuring the temperature at which it started to melt and the temperature at which it ended melting, and using that temperature difference to do some calculations about the purity of the sample. Okay, phase diagrams. Remember those? PV diagrams? Or we had the pressure, temperature as well, I think it was. So we had different diagrams to illustrate processes. We spent a lot of time with the PV diagram, where we put pressure on the vertical axis and volume on the horizontal axis, because when I have a transition, if I have a transition like that, what would we name that kind of transition? Isobaric. Okay, isobaric, because the pressure stayed constant. And I can calculate the work done for that, because work is equal to P times change in volume. So isobaric is really easy to calculate the work. The next one I'm going to draw is even easier. What kind of process is that? It's supposed to be a straight vertical line. Isochoric, constant volume. How much work do I have for that? Yeah, that was 0 because delta V equaled 0. But then we have other ones that are more complicated, things that go like this. Well, I shouldn't have used that color since I was. You kind of have to have them tell you if it's isothermal or adiabatic, because we have both of those processes that we deal with, and they have subtly different shapes. How do I find the work done in a cycle that goes like that? Okay, if I want to get the exact right number, I'm going to have to use calculus for the one that's adiabatic or isothermal. So let's go to something that's neither adiabatic nor isothermal. Let's say it went like this, a straight line. How would I find the work done in a single cycle? I take the area enclosed by the cycle. Because since work is pressure times change in volume, I can make all the little slices, and each one has a pressure times change in volume, add them all up, and it's the total. So the area that's enclosed here is the total work. If it's clockwise, like I showed, is that a positive work or a negative work? It's got to be one, and it turns out it's positive. It's a positive work done by the system. So clockwise, positive work done by the system. Counterclockwise, negative work done by the system. We talked about heat engines, coming up on the next slide, of course. And with heat engines, if you're trying to get out work, it better be a clockwise cycle. But then we had refrigerators. Refrigerators, you put work in to move the heat. Well, that's going to have to be a counterclockwise cycle because you're putting work in instead of having work done by the system. So you could just look at a PV diagram. If it shows you a cycle in the direction it goes, you could say if that's going to be working as a heat pump / refrigerator or as a heat engine, just based on if it's clockwise or counterclockwise. Okay, we've already talked about these in brief. Conduction, when you have direct contact between things, heat can transfer between them. Because you basically have molecules that are moving in this one, they collide with molecules moving in this one, and those collisions will then transport energy. Convection is an intermediary, such as air comes and touches my skin, gets heated up because I'm hot. Heat flows out of me into that air. Because heat flows out of me, I feel a little cooler. And then the air is hot, it expands. Because it's expanded, it's less dense. Because it's less dense, it floats up. And that's a convection cycle then. Radiation is electromagnetic radiation. We have the Stefan-Boltzmann law that I used on the preceding page to solve the homework problem. Wien's law, I don't think we spoke about Wien's law, so we won't worry about it now. We'll worry about it next semester when we talk about light. Okay, last chapter, chapter 15 on thermodynamics. We have 4 laws of thermodynamics, starting with the 0th law. So what was the 0th law of thermodynamics?
A equals B, B equals C, then A equals B.
Okay, if object A is in thermal equilibrium with object B, and if object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. And since in thermal equilibrium means you put them in contact and no heat flows, and one statement of the 2nd law of thermodynamics, okay, I've got 2 of them written here. The Clausius statement says that heat flows from the hotter one to the colder one. If I put 2 things in thermal contact and no heat flows, that means that neither one is hotter or colder. Ergo, they're the same temperature. So with the 2nd law's understanding, you can come back to the 0th law, and that means if temperature A equals temperature B, and temperature B equals temperature C, then temperature A equals temperature C, and that's just obvious. And so it was codified as law after the other ones because it was too obvious. Nobody ever thought you'd have to make that a law. But when they started understanding more about what temperature was, after things like that kinetic theory of gases derivation for temperature, then they came to the realization we need to be more specific about this. So 0th law, just ask Rachel, not during the test though. 1st law, what's the 1st law of thermodynamics? Energy cannot be created or destroyed. It can only be converted from one type to another. So we have things like a nuclear power plant. The nuclear power plant is not, quote, generating energy. It's converting energy from one type to another. So we use kind of improper terms there. What they're generating is useful energy from energy that wasn't all that useful to us, right? The stability of the nucleus of an atom isn't directly accessible to us. I now have a problem because my wife gets accessible and accessible confused. And so now you are who you talk to, right? So, where was I before? Okay, so the power plant is converting energy from a type that we can't really use to a type that we can. It's basically a type of heat engine, converting energy in the thermodynamic sense into mechanical energy that we can use. Okay, 2nd law of thermodynamics. Got 2 statements here. The first one, heat naturally flows from hotter to colder. The second one, the entropy of the universe never goes down. It only goes up. You can have an isolated, if you have an isolated system, the isolated system is going to have the same rules. If you have something that's not isolated, like water in a refrigerator, the entropy of that water can go down. In fact, that's what that problem with the lava is really trying to teach you. It's having you do calculations. It's trying to show you that as the lava goes from over 1,000 Celsius down to 700 degrees Celsius and then solidifies, what's continually happening to the entropy of the lava? Which way is it going, up or down? It's going down. Or in the parlance of the general populace, it's becoming more ordered. When it solidifies, the atoms are stuck in positions that's more ordered than moving around. What's happening to the water at the same time? You have heat flowing out of the lava into the water. So the water is gaining energy, which is raising the entropy of the water. And if this second law, if the entropy statement is correct, what should you get for the sum of the entropy of the lava or the entropy change of the lava and the entropy change of the water? It's going to have to be greater than or at the very least equal to 0. In reality, it's always going to be greater than 0. I didn't really talk about reversible processes. Reversible processes is a process that has, by definition, no change in entropy, so it can go either direction without violating the second law. The Carnot engine uses reversible processes. They have to be constantly in equilibrium, and that's why the Carnot engine is not possible, because it would take an infinite amount of time for it to be constantly in equilibrium and go through the reversible processes. Yes, I want to mention one more thing here about entropy. Entropy is sometimes called times arrow. And the reason it's called times arrow is because entropy tells us, it's the only thing in physics, believe it or not, that tells us the direction a process has to go. We could, borrow your water bottle. According to every law in physics except for the second law of thermodynamics, I can have this water ball sitting here, and suddenly I can have the water in here freeze and the surface that's sitting on get really hot. That is perfectly acceptable by every law of physics except the second law of thermodynamics. Because the second law of thermodynamics says that heat is not going to flow from the colder into the hotter naturally. If it did that, that would cause us to have a global decrease in entropy. And so the second law gives us directionality. And we often have problems about, consider an egg. If you take that egg and you fry it on the pan, you can never take it and reverse it to get back to the egg because you have gone to a higher entropy state and you can't lower the entropy back. Right? We make statements like that, but it's a process that, when you think about it, becomes pretty clear about why that second law gives us a direction for things to travel. And that leads to a philosophical dilemma, the idea of heat death. If you take a heat engine, what did you have to make a heat engine work? You had to have heat, but heat specifically you had a high temperature and a low temperature. If you had no temperature difference, you couldn't make a heat engine. You have to have a temperature difference. But every time you run a cycle of that heat engine, you're exhausting more heat into the cooler one. So what's happening to the temperature of the cooler one? Heating up. And you're taking heat out of the hotter one, so its temperature is going down. So your temperature difference is constantly getting closer and closer to 0. And the concept of heat death is everything in the universe, if you really get down to it, is a heat engine. Whether we're talking about expansion of the universe or the engine in an automobile, they're all heat engines. And so everything is working toward coming to equilibrium at temperature. And if everything reaches the same temperature, don't worry that we'll be incinerated at that point. If everything reaches, I say that, I haven't done any calculations, it depends on your model for the universe, if we're all incinerated or if we're all frozen. Probably not going to be comfortable at any rate. But if everything reaches the same temperature, you no longer have something that you can harvest energy from. And so at that point, they say you have heat death. You can no longer make a usable heat engine. And then it becomes theoretically impossible for life to exist. Good to know, right? Yes. Okay, heat engines. What's the purpose of a heat engine? Okay, to convert thermal energy into work. So it's to do work. I'm happy with your answer. The efficiency is defined as, and we had a homework problem that used eta instead of E. It's defined as what you wanted out. So you want work out divided by what you put in. Well, you put in heat. Did you put in heat at high temperature or low temperature? You put in the heat at high temperature. You might say, well, what about the exhausted heat? Doesn't that count? Not in this equation. Because it didn't cost us anything for the exhausted heat. That was just wasted energy. What we had to, when you're buying gasoline, you're not also buying the exhaust that comes out of the engine. You're only buying the gasoline. You're only paying for the heat at high temperature. So the efficiency is the workout divided by the heat at high temperature you put in. Now we have this Carnot cycle. The Carnot cycle with its isothermal expansion, its adiabatic expansion, its isothermal compression, its adiabatic compression. What's special about the Carnot engine? Okay, it's the most efficient you can have. It's what we call the ideal engine. So if you have a problem that says ideal, and it's talking about a heat engine, whether it's a heat pump or a heat engine, if it says ideal, it means it's the Carnot cycle, which isn't physically possible, but it's a theoretical standard that tells us what's the best efficiency we could possibly get. And so we have that Carnot efficiency, and it turns out the Carnot efficiency is going to be that first one is always going to be the result of work over QH. But it can be written as temperature hot minus temperature cold over temperature hot. Or 1 minus temperature cold over temperature hot. And so the Carnot efficiency allows you to very quickly calculate, this is the maximum theoretical efficiency I could get with these temperatures to start with. And so that's the usefulness of the Carnot cycle, telling you what the theoretical best is. Now, you had a homework problem that dealt with the Otto cycle, and that's a different cycle that has what? Isocore and can't remember if it was adiabat. I think it was adiabat. Isocore, adiabat. Or we have the diesel cycle, which I didn't look anything up. I went through and did the answers, and I was like, I don't know. Tried to match the diesel cycle to the Otto cycle. That was wrong. We have these different cycles that have efficiencies that are always going to be less than the Carnot efficiency, but you can try to aspire to the Carnot efficiency. For heat pumps and refrigerators, what's the difference in a heat pump and a refrigerator?
Heat pump pumps heat in, refrigerator takes heat out.
Okay, so I always think of a heat pump or a refrigerator as a conveyor belt. You're putting in your work, and that work is moving heat. So I have the Q cold is going to Q hot. Not the way heat's supposed to go, right? It's because we're putting in the work that we can make it go the opposite direction. And because of a balance of energy, we're going to have that the actual Q hot is the work we put in plus the Q cold. Right, so you add them together here for the Q hot. In these, they're always going to be more than 100% efficient. That is, the worst possible heat pump would have an efficiency of 1 because it's not actually converting the work into heat. It's moving heat. And so we talk about the coefficient of performance, which is equal to what you want out divided by what you put in. Well, what you put in is always going to be work, but what you get out is going to be either Q hot or Q cold, depending on if you're using it as a refrigerator or as a heater. So the coefficient of performance has two different equations, simply depending on if you want to maximize cooling or maximize heating. Okay, we're out of time. Next time I see you, it'll be test time.